In this video, we're going to be talking about how to use Lagrange multipliers to find the extreme values of a function. And in this particular problem, we've been given the function f of xyz is equal to xyz, and we've been asked to find the extreme values of this function, assuming that the function is subject to this constraint equation, x squared plus y squared plus z squared is equal to 3. Now this Lagrange multiplier problem might be a little bit more complicated than others because our original function is a function of 3 variables, x, y, and z, and we've only been given one constraint equation. More often we're given a function in 2 variables, f of x and y, and then one constraint equation, and sometimes we're given a function in 3 variables and 2 constraint equations. But in this particular problem, we only have one function in 3 variables and one constraint equation to work with, and we need to use just this information to find the extreme values of this function f. The good news is that we're going to follow the same kind of process we always follow with Lagrange multipliers. The first thing we're going to do is convert our constraint equation to a function of g in terms of x, y, and z, and we're going to do that by subtracting 3 from both sides to get everything on one side. So we're going to end up with g of x, y, z is equal to x squared plus y squared plus z squared minus 3. So now we have everything on one side, and we have a function for f and a function for g. Now, because we're going to use Lagrange multipliers, what we need to do is take partial derivatives of both functions with respect to each of our 3 variables, and then we're going to take those partial derivatives and set them equal to each other, but we're going to take the corresponding partial derivative. So we're going to take the partial derivative of f with respect to x and set that equal to the partial derivative of g with respect to x. We'll do the same thing with the partial derivatives for y, and we'll do the same thing with the partial derivatives for z. The only thing we have to remember is that we always multiply the partial derivative with respect to g by the Greek letter lambda, because that lambda value is our Lagrange multiplier. So here's what that's going to look like. We're going to take the partial derivative of f with respect to x, which is just going to be yz, and we're going to set that equal to the partial derivative of g with respect to x, which is just going to be 2x. We treat y and z as constants, so we're going to get 0, 0, and the derivative of a constant is just 0, so we just have 2x. But then we have to multiply 2x by lambda, so we're going to get 2x times lambda. Now we're going to do the same thing with the partial derivatives with respect to y. So the partial derivative of f with respect to y is just xz, and the partial derivative of g with respect to y is 2y. Then we multiply our result here on the right-hand side by lambda. Now we take the partial derivative of f with respect to z, and we get xy. Taking the partial derivative of g with respect to z, we get 2z, and then we multiply our result by lambda. Now once we get to this point in the Lagrange multiplier process and we have these 3 equations, our goal is to solve each of these for a value of lambda. If we can solve all 3 of these for lambda, then we can set all 3 of them equal to each other and find a relationship between x, y, and z. So this lambda variable here is just a tool that we can use to find a relationship between x, y, and z. So there's a couple different ways that we can go about that, but probably the easiest way in this particular case is to multiply here this first equation by x, both sides by x, the second equation both sides by y, and the third equation multiply both sides by z, because when we do that, we're going to end up with xyz on the left-hand side of each one of these equations. So let's go ahead and see what that looks like. Multiplying the first equation on both sides by x, we're going to get xyz is equal to 2x squared lambda. The second equation will get xyz is equal to 2y squared lambda when we multiply both sides by y. When we multiply both sides of the third equation by z, we're going to get xyz is equal to 2z squared lambda. Now what you can see is that we have x, y, and z on the left-hand side of each of these 3 equations. What we can do is divide through each of these equations by lambda on both sides, and what we'll end up with is just xyz over lambda on the left-hand side of each equation, and the lambda will cancel from the right-hand side of each one of these equations. So now we say xyz over lambda is equal to each of these values. Since all of the left-hand sides are equal to one another, we know that the right-hand sides are also equal to one another, so we can drop the left-hand side and we can say 2x squared has to be equal to 2y squared, which has to be equal to 2z squared. And now you can see we've eliminated the lambda variable and we have this relationship between x, y, and z. So we can divide through this entire equation here by 2, and we can see that x squared is equal to y squared is equal to z squared. And now if we go through and we take the square root everywhere, we can see that x has to be equal to y, has to be equal to z. So now we have this relationship between x, y, and z. We've eliminated our lambda. And at this point, we want to take the relationship that we found between x, y, and z and plug it back into our original constraint equation. So taking partial derivatives of f and g and setting them equal to each other while including this lambda constant here generates these three equations that allow us to find a relationship between x, y, and z. But we're really dealing with 4 equations at this point, these 3 partial derivative equations plus our original constraint equation. So we always think about those 4. We use these first 3 to solve for a relationship between x, y, and z, but then we always bring that relationship back to our original constraint equation. Because at this point here, we just have x equals y equals z, so x, y, and z could be any value. We need to find out which particular values of x, y, and z represent extreme values of the function. So what we do is plug this relationship back into our constraint equation. Because x is equal to y is equal to z, we can go ahead and plug x in for y and z to this constraint equation, and we'll get x squared here. Plugging in x for y, we'll get plus x squared. Plugging in x for z, we'll get plus x squared is equal to 3. So we see that 3x squared equals 3, and we know that x squared is equal to 1. Taking the square root of both sides, we can see that x is equal to positive or negative 1. And now knowing that we have this value for x, we can plug it back into the relationship we found between x, y, and z, and we can say that we have 2 critical points of our function of f. One point is 1, 1, 1, because we take the positive 1 value and we say x equals 1, which means y has to be 1 and z has to be 1. Or we say x is negative 1, which means that y and z have to be the same, so we have the point negative 1, negative 1, negative 1. So these here are 2 critical points, and all we need to do is plug these 2 values back into our original function, f of xy, to see what values we get back. So if we go ahead and do that, if we say f of the point 1, 1, 1, we plug it in here, we're going to get 1 times 1 times 1, which is equal to 1. If we plug in negative 1, negative 1, negative 1, we'll get negative 1 times negative 1 times negative 1 is just a negative 1. So we know that these critical points represent extreme values of our function f of x, y, z. Now that we see the value of the function at these critical points, we know that this point, 1, 1, 1, represents a local maxima, because this value here is greater than this value here. So because 1 is greater than negative 1 and both of these critical points represent extrema, we know that this has to be the local max, and we know that this has to be the local minimum of the function f of x, y, z.